Hi, today I'm going to discuss the solutions for Atcoder Beginner Contest 374 Problems A to F. Let's start with problem A. For this problem, we're given a string consisting of lowercase English letters, and we're supposed to check whether the string ends with san. And if yes, we just print out yes, and if not, we print out no. So for this problem, we can just directly check whether the string ends with san. So let's look at the code for this problem. We first just input the string, and then we just use the substring function to check if the last three characters of the string is equal to san. And if yes, we just print out yes, and if not, we print out no. Let's look at problem B next. For this problem, we're given two strings, and we're supposed to check if they are equal. If they are equal, we print out 0. Otherwise, we would print out the first position where the strings are different. So for the first sample input, the answer would be 3 because C and E are the first characters that are different from each other. Let's look at the code for this problem. We first input the two strings, and then we can just check if the two strings are equal. If they are equal, we print out 0. If not, we can loop through the maximum length of the two strings, because if one length is greater and the other is shorter, then they will also be considered not equal. And in this case, if one of the lengths is already less than or equal to I, then we would just print out I plus 1, because this means that this is already the first character that is not equal. Otherwise, if the characters aren't equal, we will also print out the answer. For problem C, we're given n departments, each with ki people in it, and we need to assign each department to either group A or group B. And we're supposed to try to minimize the maximum value in the two groups. So let's look at the algorithm for this problem. For this problem, the first algorithm that comes to mind is a brute force algorithm that just checks if each department is in group A or group B. And we notice that since n is really small, only 20, this algorithm will work because it can be done in the time complexity of 2 to the power of n. So we can do this with a bit mask that maps 1 to group A and 0 to group B. So, for example, when n is equal to 5 and the bit mask is equal to 10110, departments 2, 3, and 5 correspond to number ones. So they would be in group A. And departments 1 and 4, these two, would correspond to group B. Let's look at the code for this problem. For this problem, we first input the number of people for each department, and then we just loop through all the possibilities. And so this part is checking whether the bit mask for each number is equal to 1 or 0. So we loop through the n departments, and we just check if each place is equal to 1 or 0. If that place is equal to 1, we add them to the count for group A, and otherwise we add it to the count for group B. And afterwards, we just try to minimize the maximum value of these two groups. For problem D, we're given n segments, and we're supposed to draw the n segments using the laser. And in this case, the laser will move at t units per second when it's drawing the segment. Otherwise, when it's just moving between different points, the laser will move at s units per second. And we need to find the minimum time that we need to draw all the line segments. And in this case, the time would just be the time to draw the segments and the time to move between the points. So let's look at the algorithm for this problem. For this problem, we again notice that n is really small. In this case, it's only 6. So it is possible to enumerate all the possible orders to draw the line segments in, and also the starting locations of each of the line segments. And to enumerate the orders, this would take a time complexity of 6 factorial. And since there are 2 possible starting locations for each of the line segments, and only a maximum of 6 line segments, then this takes a time of 2 to the power of 6. And we notice that this would fit in the time complexity. So let's look at the code for this problem. The first section is just inputting all the values. And the second section is to loop through all the orders that the line segments can be drawn in. And this part is just a bit mask to loop through all the possible starting and ending locations for the line segments. And so the distance that the laser will need to move between points is just from the starting location to the start of the first line segment and the end of the first line segment to the start of the second line segment, and so on. So this part is just calculating all the distances that the laser would need to travel when it's not drawing the line. And so the getStart and getEnd functions just returns the starting and ending locations corresponding to the current bit mask. So for this part, when the bit mask is equal to 1 for that location, the getStart would return A, B, and otherwise it would return C, D. And in this case, the getEnd would return C, D, and return A, B when the bit mask is equal to 1. And the dist function is just to calculate the distance between any 2 points. And afterwards, this part is just updating the answer. And when the laser is drawing the line segments, it would draw in t units per second. So we can divide the total distance traveled when it's drawing the line segment by t. And when it's just moving between 2 points, it moves in s units per second. So we can divide the count by s. And afterwards, we just need to print out the answer. For problem E, we have n processes, and for each process, we have 2 types of machines, S and T. For machine S, it can produce A products in P dollars. And for machine T, it can produce B products and cost Q dollars. So for each process, we want to try to maximize the production capacity. And in this case, the production capacity is just the minimum number of products that all the processes can produce. So let's look at the algorithm for this problem. The problem asks us for the maximum production capacity. And when we see questions like this that ask for the maximum or minimum, we can think of binary search. So for this problem, we can do binary search on the maximum production capacity W. And for the check function, we notice that there are two machines, so there is always one machine that is more cost efficient. Each process has machine S and machine T, and machine S produces A products for P yen, and machine T produces B products for 2 yen. And if we purchase B type S machines, then we can produce a total of A times B products. And similarly, if we purchase A type T machines, it would produce a total of B times A products. And this means that the less cost-efficient machine can just be replaced with the more cost-efficient machine to reduce the price. And since A and B are at most 100, this means that for the less cost-efficient machine, there's at most 100 of them. So for the check function, we can just directly loop through the number of less cost-efficient machines and calculate the number of more cost-efficient machines needed. And afterwards, we can just count the minimum cost needed to buy the machines. So let's look at the code for this problem. The first section is just inputting the values and also checking which machine for all the processes is more cost efficient. So we would swap the values so the least cost efficient machine would be on the second. And this part is just doing a binary search on the maximum capacity. And for the check function, we loop through all the processes and keep track of a minimum cost for each of the process. And this loop is just looping through the number of less cost-efficient machines that we buy. So this part calculates the remaining, which are the products that would be produced by the more cost-efficient machine. And afterwards, we just sum up the costs. And this part is because if our sum is already greater than our budget x, then we return false for the check function. And otherwise, we will return true. So afterwards, after we do our binary search, we can just output the answer. For problem F, we have n orders, and each order will be placed on day Ti, and we need to ship the orders according to these following rules. So at most k orders can be shipped together, and each order can only be shipped after the order is placed, so after day Ti or later. And so once a shipment is made, the next shipment needs to occur after X days. So each day, the customers have dissatisfaction values. So if the order is shipped at day Si and the order is placed at day Ti, then the dissatisfaction value is Si minus Ti. So we need to minimize the total dissatisfaction value. Let's look at the algorithm for this problem. For this problem, the first solution that comes to mind is a dynamic programming approach that has two states, I and j. The I represents the first I items and j represents the time. So dpij will represent the minimum dissatisfaction to ship the first I items before time j. However, time is up to 10 to the 12th. So this is too large for the memory and wouldn't work. However, afterwards we noticed that we don't have to record all the times because the shipments can only occur after at least X days after the previous shipment. So we can change the second dimension, which is the time, into a map. So the DP transition will occur as follows. If C is the current time and L is the number of orders that are sent together, and prev is just the previous dissatisfaction value, which is I minus L orders, and the time is before C minus X. So this ensures that there's at least X days in between all the shipments. So DPIC would just be the previous value plus the new dissatisfaction gained from this current shipment. So if we want to calculate the value for the dissatisfaction quickly, we can use a prefix sum. So the sum would just be the sum of the time that the orders are placed. So the new dissatisfaction would be calculated as the current time times the number of orders that are sent together minus the sum of the times, which are the time that the orders are placed in this range of values. So this can be calculated quickly, and afterwards let's look at the code for this problem. We first initialize a DP for which is a array of maps, and so we first input all the values and also calculate the prefix sum for the time that the orders are placed. And so the initial state for the DP, which is at if 0 orders are sent and it's at time negative X, then this will have a dissatisfaction value of 0. And afterwards, we can loop through the first part. And so if I orders have been shipped, we can loop through, like J is the number of orders that are shipped together in this current shipment. So the number of orders is just the minimum of K and I. And so afterwards, we can loop through the possible times that the shipments are sent in the previous shipment, which is in DPI minus J. And so the time C for this current shipment would just be A, which is the previous time for the previous shipment, plus X, and maximum with the current order, because the shipment will need to occur at least after this order and also after A plus X. So if the map already contains the value, the time C, then DPIC would be the minimum of DPIC and the transition state that we mentioned previously. So this part is just the previous value, and then this part is just the new dissatisfaction. So to calculate the answer, the answer would just be the minimum value of dpn, and so this means that n orders have already been sent, and we need to find the minimum dissatisfaction that this occurs. So afterwards, we just print out the answer.